Hello and welcome to this afternoon session on deep recommendation systems. My name is Oliver Gindele, Head of Machine Learning at Datatonic. And in case you don't know us, Datatonic is a boutique consultancy based in London, and we solve bespoke problems in big data and machine learning for clients across many industries. We're a Google Cloud Premier partner, and we support some of Google Cloud's largest clients in the UK, especially in retail and in media. And in this session, I'm going to show you some of our findings and experiences on how we build recommender systems for these clients. I'm going to start quite simple and easy with a very common approach to product recommendations, show how this can be put into TensorFlow, and then end with some of the more recent advances in deep learning and how they can enhance production recommendation systems. The good thing about talking about recommendation systems is everyone is very familiar with them already. Most of you will know Netflix or Spotify, and you're very used to how they present content information to you as a user. And the goal of a recommendation system is quite simple. As a user, I don't want to scroll through hundreds of thousands of songs to find the ones I like, or use awkward filters to narrow down my search. I want to have the content and the products presented to me that I know I'm going to enjoy. So Netflix and Spotify both do this in their own ways. Discover Weekly is probably a very good example on a personalized, curated list of recommendations. There are some less obvious cases of recommendation systems that you're quite familiar with, I believe. One is Google Search. If I go on Google and type in Python, this is what I see. This might not look very, on the first glance, this doesn't look very suspicious. But if I were to search for the snake, the animal python, I actually would need to scroll down and press on page 2. So even Google Search is heavily personalized. So let's start with a very common and popular approach of building recommendations, which is collaborative filtering. It's been heavily used in industry for over 10 years, and it basically works as follows. We have a matrix of M users and N items, and this can be arranged like on the left side here. And what we have in this case is ratings. So a user would rate items they've seen. Quite often this rating matrix is quite sparse. It has a lot of empty fields because users only have time to read so many books and they're never going to rate all of them. So the recommendation problem is to now fill this matrix. Let's see and hope that this holds. So we want to fill this matrix and basically find the items that users will give naturally a high rating to without them having to explicitly have the interaction and seen the product before. The collaborative filtering way of doing this is splitting this matrix into a user-based matrix and an item-based matrix with a lower dimensionality. This is a lower rank representation, and we basically condense this space into something of dimension k. And what we want these two matrices to learn is some latent representation of user space and how similar users are, and item space, or equivalent, how similar items are. What we can then do if we find this representation is we can take the dot product between a row and a column and then generate a rating that hasn't existed before. So we estimate ratings and fill this matrix out one by one. Once we achieved and gathered a few of these ratings, we can sort them, take the 5 highest, and serve them as recommendations. To put this into a more concrete form, what we want to solve is basically this loss function here, where we have a ratings matrix over users and items. We have a user matrix, xu, and an item matrix, y. And we want this dot product to approach the real ratings as close as possible, so we optimize the square form of this. We can add some regularization as well to avoid overfitting. There's many ways to solve this. It's been popularized almost a decade ago by winning what was called the Netflix prize, a big recommendation challenge with a winning prize of 1 million. And the nice thing is you can solve this with singular value decomposition quite straightforwardly, or you can parallelize the approach and really run it on large data sets, because you quite likely have millions of users and tens of thousands of products, so the matrix is quite large. What you can use is alternating least squares or stochastic gradient descent, which we'll get to in a bit. So this was a rather abstract introduction to recommendation systems. Let's put this into practice. And what better use case than finding love with numbers or actually matching dating profiles? I found a public data set on online dating profiles or ratings of thereof from a web page called Libimseti. It's a Czech web page. Does anyone know this actually? Don't see any hands. And this is how the web page looks like. They released a sizable data set over 10 years ago in 2005, but this is actually how the web page looks today. I only taken this screenshot a few months back, and it still has a few hundred of active users. Let's have a look at the data before we do any modeling. It covers almost 18 million rated profiles with over 100,000 active users. And the ratings range from 1 to 10. And it has a much higher proportion of female profiles being rated, which you see on this chart on the left, that represents the histogram over the ratings split by gender. And there's one thing I'd like to point out here, because I think it's quite interesting. The distribution is sort of trimodal. There's a big broad peak in the middle. There's a huge number of zeros being given to profiles, and an even bigger number of 10s given to predominantly female profiles. So there's an interesting gender split in rating 10s versus zeros. I want you to pay attention now to the format of the data, which is on the right-hand side here. And this is quite typically what we get in a recommendation scenario, where we have a user ID, a profile ID, a rating from 1 to 10, and with this data set, we also have the gender. So to put this into practice, we're going to use TensorFlow. And I want to showcase some of the more recent advances in the TensorFlow API that make building models and training them a lot easier. I'm going to specifically talk about the dataset API and the estimator API. Is anyone already familiar with these two APIs? There's a few hands, which is great, so hopefully you can take away something new. The dataset API is what its name suggests, concerned about data feeding. And it's an abstraction over your data set. Could be CSVs, JSONs, or TF records. And what you do with it is you point it to a data source and create an iterator out of it. But TensorFlow will actually make sure the data is fed as performantly as possible. So you can use multiple CPUs. You can deal with data that's larger than it will fit in your memory. And you can do a lot of nice things to make sure that a GPU or a TPU or any accelerator use is not starved and has to wait for the CPU to do the data I/O. So that's convenient, and it also interfaces very nicely with this estimator API. The estimator API is basically a wrapper that simplifies your training loop and your evaluation loop. In the old TensorFlow ways, you had to create a session and then loop over your n steps and then calculate gradients, update them, etc. And this had all to be defined quite manually. These days, you write the model, you put into the estimator, or even easier, you use one of the pre-made ones. There's already quite a variety of deep neural network estimators, linear models. And what you can do then is, in scikit-learn or Keras style, you run .train or .predict, and TensorFlow will take care of the whole training loop. What's more, you can use the estimator to do distributed training. So you can run it across multiple nodes with multiple accelerators each. Let's say a dozen of nodes with 8 GPUs. You don't have to write any code for that. The estimator will do it out of the box. So you can easily scale TensorFlow on systems like Cloud ML Engine on Google or Kubeflow. The estimators, obviously also a nice way to package models. And there's already a lot contributed by the community. So you'll find booster trees, Gaussian mixture models, clustering methods, even time series models these days, pre-built as an estimator in TensorFlow. There's a last piece in the puzzle, which is the feature columns, which basically is a way to map your input data to tensors in a TensorFlow model. And the two main categories here are categorical columns or dense columns. And it's a way to specify whether your input data is numeric or a category or should be in a bucket, etc. And then TensorFlow, with that API, will take care of one hot encoding and representing it in the correct way. So that's a neat way to point to your input data and make sure TensorFlow handles it correctly. Now that we know the pieces of the puzzle, and we also know the objective function I showed you before to build the recommender system on the online dating data, we can start by parsing the data. Enter the dataset API that I just mentioned. We build the so-called input function, and I want to jump right to the middle. We can just build this over a data file with as a text line dataset. Then we take a few steps, can be quite bespoke. We shuffle, there's some caching, repeating, and prefetching. But something really important happens in this line here where we apply. We map a function on every row and we batch it up afterwards. But in this mapping, we actually decode the CSV, which happens up here. So this is the whole decoding of the CSV, and this might be quite data dependent, subject to how your CSV file looks like. The cool thing is this can be done in parallel, so you can really exploit all your CPU cores if your CSV is sharded. And you can easily also read from cloud storage, distributed storage like Hadoop file system, etc. Input data reading done. Let's move to the model, the arguably most interesting part. Recall that we want to split and factorize this matrix of ratings into user-based matrix and item-based matrix with a lower space representation. And this is what happens in this upper part here, where we first parse the user ID and the profile ID as some categorical column. And what we then do, after we parse it as a one hot encoder column, we run this embedding on top. This is quite crucial because now we take this sparse vector and represent it as a dense vector. And we actually have a specific dimension k. This 10 dimension of 10 is exactly the dimensionality k that is the lower space representation that we want to find. And basically this is a hyperparameter, so I just choose 10 here. And we do this for our both columns, user ID and profile ID. I'm also going to add some bias terms. Haven't shown this on the loss function before. And we're going to move them into tensors with this input layer function and then do some splitting for convenience. But now we represented the IDs of users and profiles into a 10-dimensional space. So we can start learning these two matrices. And that's by setting up the loss function. So we do the dot product between user ID and profile ID. We add a bias for users, a bias for profiles, add some regularization as well, and then take the mean squared error. That's all there is to it. Now we have the model, we have the data set. Let's put it into this estimator wrapper. At the top, we can define some evaluation metrics. In this case, root mean squared error and mean absolute error. We optimize the loss with ADAM, or a derivative of SGD. We put this into an estimator spec here, and then lastly into an estimator. And now all there's left to do is run .train. One last thing, I used TensorFlow layers here to define, or some TensorFlow core API functions to define the model, but you could also use Keras and then pass a Keras model into an estimator. It works the same way. So this was all nice. I showed you the simple version of collaborative filtering and how it can be represented in TensorFlow. But the question is, can't we go deeper and use deep learning to solve a similar problem? So what I showed you previously was this left side from a paper 2 years ago, which is called generalized matrix factorization layer, which is the same as I just showed you in code, with this element-wise dot product between user embeddings and item embeddings. But how would it be if you just build a multi-layer perceptron, a few feed-forward network layers, and let them act on the same embeddings, or actually separate embeddings in this case, and then take the output of both matrix factorization and the MLP, concatenate it, and calculate a loss upon that. That's not just nice because it's deep learning and it's very cool to do. It actually gives a lot of benefit. One is people struggled for a decade to enrich matrix factorization methods with metadata, with data such as demographics, other user and content information. The multi-layer perceptron way is quite straightforward to add that data. So what we can do is we can input gender that we've had, or if you want to build a movie recommender system, you can input features like the category, could be search tokens, it can be movie length, etc. So now we found a way to also make use of potentially a lot more data than traditional matrix factorization approaches would allow. So how well does that do? What I plot in this table here is the RMSE error and the mean absolute error. And I do this for matrix factorization alone. The multi-layer perceptron all by itself, so the right-hand side of the model on the last page. And then a code-trained version that I just explained to you. And also compare it to some paper I found, a decade-old paper on the same data set. What you'll see is MLP already improves the matrix factorization quite slightly. And bear in mind that the gender term is included here. But combining matrix factorization and the deep network actually yields the best results. On RMSE alone, it actually beats the research paper I found. And this was built, the network and the architecture, with very little hyperparameter tuning. So we already found a way to make matrix factorization possible in TensorFlow and to extend it with deep neural architectures to achieve quite decent results. Question is still, can we do any better? There's 4 ways to do that, and we're going to start with better and more data. What that means is, if you do recommendations in retail especially, you will sit on a database that sort of looks like this and is often called a single customer view, where you have information on transactions and purchases, but also personal details, demographics, maybe product catalogs. What we work a lot with clients is to establish this lower part, the blue tabs, where we use this to proactively score and predict, such as propensity scores, whether someone will buy a service, product recommendations, or other values like lifetime value, sentiment scores, etc. And this then enables a lot of downstream applications, such as product recommendations, but also more targeted advertising, etc., and you name it. The point I want to make is, sitting on data is very important, and curating this even more so. So if you're new to product recommendations and or machine learning, the biggest ROI is improving this and probably ignoring what I'm going to tell you in the next 10 minutes. So data aside, there's a few other ways to improve the models I just showed you. The first target will be loss functions. So what we looked at before is the loss function that's basically a regression loss. We compare the rating from the actual data versus a reconstructed rating and just take the squared error of that. Issue with that is usually we don't have ratings. There's multiple reasons for that. Users are usually quite lazy and you don't want to give a rating. And even if you give a rating, it might be heavily biased. We saw that online dating data set where the rating was sort of trimodal and it's not nicely normally distributed, and it already gives an indication that people usually rate either a 0 if they have a complaint and really don't like something, or they give it full marks. But the space in between is usually quite empty. Also, a lot of services just won't allow you to give feedback in forms of ratings. Even Netflix actually reverted from a star rating to just thumb up, thumb down. So ratings might not be available for your recommendation system, but that doesn't mean you can't build one. What you do is you can use implicit feedback. This is the first improvement on a loss function. And instead of a ratings matrix, we construct an interaction matrix of implicit feedback. And this could be a click on a product, or a product being placed in a basket, or an actual purchase. And you want to weigh all these interactions differently, where a purchase is probably a lot more meaningful than just a click. So you have a matrix P over user and items again, and this contains the interactions. And you can weigh this with your matrix C that has this weighting of what you think is important in the way you model customer interactions. The rest of the loss function will be quite the same, and with this you can train on pretty much any transactional data. It still leaves you to define this weighting and looking at your data and figuring out how much more is a purchase worth than a click. One other way to avoid this is actually a classification loss, or you can use it as a logistic regression, and you just apply this logistic function on top of your loss and you scale your predictions between 0 and 1. And it's either going to be no interaction or an interaction, and you don't care how you got there. Lastly, these two and the previous loss function, they all pairwise losses or pointwise losses, where you compare an estimate versus the real data. But you could actually be a lot smarter and improve a ranking loss directly that not just reproduces a rating or interaction score, but also reproduces how people would order several products if they would see them. This brings us nicely to improved metrics, because I can explain an important concept here. Metrics and improving them obviously won't yield better models or results, but it might allow you to judge the performance of models a lot better. And the key point here is there's no good offline metrics for recommendations. They all can be quite misleading, and a better score in an offline recommendation scenario doesn't mean it actually works in practice and in production. So the only way to really test recommender systems is online via A/B testing. But one way to move beyond just RMSE is to look at several recommendations at the same time and calculate precision at K. So imagine you recommend K or 5 products, and you hold out some data about every user. And we're back. So if you hold out the latest 5 products for every user in your data set and use it as a test data set, you can recommend these and then recommend 5 products you think are the most suitable, and then calculate how many of the ones that are actually your recommendations are going to be purchased by the user. This score is precision at 5, and a value of 1 is the best possible. But what if the order of the items also matters? If you recommend 5 products, the most important one should be at the top. So this is the NDCG, I'm not going to touch this anymore, that might help. NDCG metric comes usually from search, and it means you want to not just look at whether the products are relevant and are contained in what the user selects next. It also respects the ordering, so it means you want to put the most relevant item on top, something like you see from Google search. So this is an extension of precision at K, where the relevance is also in the ordering. And there's actually neat ways to build neural networks that optimize this as a loss function directly. So you're not going to optimize and train on replicating the best possible rating. You actually train to improve this metric and this loss directly, which can give very good results. And which is really the challenge of recommendations, where quite normally as a user you see a handful, 5 products, and you want to actually see the most relevant one on top. Metrics aside, there's one last way, and maybe the most interesting one. We can actually build even deeper architectures and be a bit more fancy and use this concept of the embeddings of this low K latent space representation. One quite straightforward way, very similar to this neural collaborative filtering approach I showed you before, is the wide and deep model. This came out of Google to make Play Store recommendations about 2 years ago. And it's very similar to what I showed you with the MLP part before. So we have a multi-layer perceptron. But instead of co-training this with a matrix factorization layer, we use just a very wide layer here. And then we co-train it as well in a similar fashion, where we combine the output of these 2 networks and optimize that. The interesting part is here, we can actually feed different features into the deep part versus the wide part. And we can use continuous features to go into the wide model and to memorize over that. And we can use categorical features such as demographics and content information to go into the deep part. And I just want to show you some results on actual data we run on a UK retailer. And we have, again, a matrix factorization approach. In this scenario, we did it with SVD. We have another matrix factorization approach with implicit feedback, so this changed loss function I showed previously. And then lastly, the wide and deep model. And now bear in mind, the metrics have changed. We're looking at precision at K and NDCG now. The data set we had a couple of billion transactions. It was a few terabytes of data, and we run these algorithms over that. And what we saw is we can improve the matrix factorization, kind of standard approach. I think we did this in Spark, with switching out the loss function and pre-processing the data differently to respect implicit feedback. And we can improve this even more, quite dramatically, in fact, if you use a wide and deep approach. So here again, and this is first-hand data we put into production, we see that deep learning with some aspects can yield very good results in recommender scenarios. One struggle there is with recommendations is that quite often a retailer or any system will have a lot of users and a lot of products, and then calculating scores for each user item combination can be quite costly. One way to avoid this is building multi-stage models, such as YouTube recommendations, where there's some input of search tokens and browsing history, which will yield some candidates at first. So there's one neural network, quite similar to what I showed you before, that again acts on embeddings of search tokens and videos, and filters down millions of possible candidates to hundreds. And this will then be fed into a second layer, or a second completely separate neural architecture that does the ranking, as I showed you before. So by splitting this into 2 parts, you can avoid calculating such big scenarios of scores. One last architecture I want to show you is the way that YouTube recommendations work these days. And again, it centers on this context of embeddings, where there's direct watch features, but there's also context, which could be time of the day and previous clicks or the browser history that Google and YouTube will collect and embed this as well. But the embedding doesn't happen as a concatenation as we previously saw, where we just embed IDs and then concatenate this all into one vector. It happens at a step of the RNN model, where we now have a recurrent neural network in action that also respects the sequential nature of this problem. And at each step, there is actually this latent cross built that will multiply the embedding into the network state or the RNN state. And this paper actually also shows quite nicely that although learning low rank representations that I showed you before can work with deep neural networks, and I clearly demonstrated that we learn good results, and this neural or deep matrix factorization approach works. But in this paper, they also show that it's quite inefficient. So actually mapping this at a different point in the architecture into your neural network, such as at each RNN step, can be a lot better approach to train neural networks. With that, I want to give you a few takeaway messages to wrap up. First, I hope I could convince you that TensorFlow is not just a library for computer vision and NLP, but you can actually express many more classical machine learning problems with TensorFlow as well. The high-level APIs, dataset, estimator, will actually allow you to build models very easily and a lot quicker than before. And it's quite straightforward to put custom algorithms or custom loss function into place, where you have a nice framework, and if you want to iterate over a few of these approaches, such as switching the metrics or the loss function, TensorFlow is a great place to do that. And I hope I could also convince you that deep architectures, even simple ones as an MLP and a simple feed-forward neural network, can already be quite useful in the recommendation scenarios. And lastly, this concept of embeddings. What I started at the beginning as learning this latent space representation that has a reduced dimensionality, that is found again in this word embedding. It appears all over the recent research, and it's a very key concept to building deep neural architectures.
Thank you for your presentation, Oliver.